The first week in August, it's piping hot in here. My smart board isn't working. Someone kicked something somewhere and I can't figure it out. So we're going to work on this whiteboard. My daughter, Abby, is in the audience, and she'll catch me if I just say something wrong or if I say something unclear. And as always, if anything is confusing, put it down on the notes on the bottom, on the comment section. Send me an email or call me or send me a tweet, all right? But let's start with number one. A shock, and that's the name of the book, with a mass of 43 grams, sits 1.8 meters from the center of a seesaw. Steve, mass of 52 kilograms, wants, the spelling is awful, to balance a shook. How far from the center of the seesaw should Steve sit? Say that 5 times fast. So, whenever you see the word balance, you should think of the word static. Things are not moving. Therefore, forces up
equal forces
down, forces right equals forces left. And since this summer, torques clockwise have to equal torques counterclockwise, or else the thing's going to move. So here's your seesaw. We got a shook over here, and we got Steve over here. A shook has a mass of 43 kilograms. Steve has a mass of 52 kilograms. A shook is 1.8 meters away. We got to know how far Steve has to sit away from the fulcrum, or the pivot, such that this thing balances, doesn't move. Therefore, forces up equal forces down, right equals left. Torques clockwise equals torques counterclockwise. Agreed?
Yes.
We know the forces up equal forces down. All right? That pivot is exerting a force of 43 plus 52. How do we change kilograms to force?
9.8.
Times 9.8. So the force up has got to be 43 plus 52, add them together, times 9.8. That's the force up. Forces up equal to forces down. There's no forces right and forces left, so don't worry about that. Now we got to worry about the torques. Steve wants to create a torque that looks like this. A shook wants to create a torque that looks like this. This one's going clock or counter?
That one's going
clock. Hello. Yo, thank you. Excellent job. They look great. I'm looking forward to using them.
counterclockwise.
Clock. This one's clockwise,
yes.
And this guy's counterclockwise. So the torque is clockwise, have to equal the torque counterclockwise. Torque is equal to two things. Torque is equal to I times alpha. We've done that 6 times in the past 4 videos. It's also equal to force times perpendicular distance, and that's the symbol for perpendicular distance. So, what torque does a shook create?
His mass times his distance away from the center.
Times his distance away from the center.
Times 9.8.
Thank you. Times 9.8. That is a torque that is counterclockwise. Can you get the bottom, Abs?
Yeah, it's just a little bit of a glare.
Okay.
It's okay.
So that has to equal the torques clockwise, and what's the torques clockwise going to be?
52 kilograms times x times 9.8.
Good. One equation, one unknown. You crunch those numbers, and Steve has to sit about 1.5 meters away. All right, 1.5 meters, that's 1 meter, that's 1.5 meters. Okay? So Steve has to sit 1.5 meters away for clockwise torques to equal counterclockwise torques, and forces up equal forces down.
Got it.
Got it? Bicycle chain wheel has a radius of 7.7 centimeters. What do we not like about meters? Centimeters?
They're not meters.
They're not meters. If the chain exerts a 35 Newton force on the wheel in the clockwise direction, what torque is needed to keep the wheel from turning? So we got a wheel that has a radius of 7.7 centimeters. So that's 7.7 divided by 100 meters. Agreed?
Yes.
0.007? 0.007?
0.077.
0.077?
Yes.
If the chain exerts a 35 Newton force at the rim, what torque is needed to keep the wheel from turning. Now that torque could be supplied by another rope over here. It could be supplied by the friction at the pivot. It could be supplied by it could be a real heavy wheel, and that's not enough to turn it. Could be a million different things. But in any event, the torque, what is this doing, clock or counter?
Clock.
So we need a counterclockwise torque that equals this clockwise torque, and what's the clockwise torque going to be?
35 times 0.077.
Make sense? So that counterclockwise torque has to be 2.7. What are my units of torque?
Newtons times meters.
Newtons times meters. Don't say newtons per meter, because that looks like this. That's clearly wrong. Newtons times meter. And by convention, a clockwise torque is positive or negative?
Positive. Negative.
50-50. A clockwise torque is negative, a counterclockwise torque is positive. So this 35 newtons, that is a positive torque, and the 2.7 newton meters is a negative torque. A rope is wrapped around a pulley and pulled with a force of 13 newtons. The pulley radius is 0.15 meters. No need conversions there, 0.15 meters. The pulley's rotational speed goes from 0. What's the symbol for rotational speed?
Omega naught.
Omega naught, or we use omega I. So it starts from rest, so it starts from 0, and then reaches a angular velocity of 14 RPMs in 4.5 seconds. What do we not like about RPMs?
They're not seconds.
They're
radians per second.
Radians per second.
Radians per second.
So 14 RPMs. RPM stands for what?
Revs per minute.
Revs per minute. We got to change that to radians per second. How do we get rid of the minutes?
1 over 60.
1 over 60. So the minutes cancel. Now we got revolutions per second. How do we get rid of the revolutions?
2 pi over
2 pi radians in 1 revolution. So the revolutions cancel. So those 14 RPMs come out to... Now what's a quick and dirty way to change RPMs to radians per second? Or RPMs, revolutions per minute to radians per second. Instead of doing all this, what do we really have to multiply it by?
Pi over 3.
2 pi over 60, or pi over 30. And if you want, pi over 30 is about equal to what? 3.14 over 30. It's about 0.1, isn't it? Does that make sense? So if I multiply that by 0.1, what do I get?
1.4.
1.4, pretty close. So if you're running out of time in May at the AP test and you don't want to do all this, to change RPMs to radians per second, all you have to do is multiply it by 0.1. That'll give you a quick and dirty for radians per second. Now I have omega initial, omega final, and time. What equation can I use to find alpha?
Omega final equals omega naught plus alpha t.
Make sense? So therefore alpha has got to equal WF minus WI divided by t. Agree?
Yes.
1.4 minus 0 divided by 4.5 gives me an alpha of
0.3.
And it wants to know the moment of inertia.
Yes.
So torque is equal to moment of inertia times
Alpha.
alpha. So the moment of inertia has to equal torque divided by alpha. The alpha we just figured out, 0.326. And the torque has got to be the force on this at 0.15 meters. And the force is 13. So that's 13 times 0.15 gives us approximately 6 kilogram
5.99, yeah.
meters squared. A little bit less, 5.9. Make sense?
Yes.